Entire books have been written on the things in the universe that are fine-tuned and look designed. For example, the expansion rate of the universe has to be fine-tuned to no less than 1 part out of 10 to the 90th power. The arrangement of the matter and energy at the start of the universe must be fine-tuned to 1 part out of 10 to the 10th to the 123rd power. This list could go on for several pages, because for life to exist on Earth, we need the just right universe, we need the just right local group of galaxies, we need the just right Milky Way galaxy, we need the just right star, our sun, we need the just right planetary neighbors like Saturn and Jupiter and Mars, we need the just right moon, we need the just right atmosphere, we need the just right plate tectonics. According to astronomer Dr. Hugh Ross, the number of fine-tuned characteristics of the galaxy, solar system, and Earth needed for life has grown from only 3 in the 1960s to over 1,000 today. So the deeper we look, the more fine-tuning we see. The more science we do, the more fine-tuning we discover. Everywhere and at every time we can currently test, we see what can be called design. In fact, it seems to be limited only by our ability to detect it. Every time we invent a new instrument to probe nature at a deeper level, we see more fine-tuning. We discover what looks like more design. The question is no longer if the universe is fine-tuned, but instead the question has become what or who is responsible for the fine-tuning. So we see design at every level, at the largest scales in the universe, at the scale of our size here on Earth, and at the scale of the atom inside the nucleus. Now, an atom is not as simple as a nucleus with electrons zooming around it like you might have learned about in high school. The protons and the neutrons, which make up the nucleus, are actually a very highly coordinated dynamic system of interactions between particles called quarks and gluons. So let's break down what actually is going on inside the nucleus of the atom. What are these quarks and these gluons doing? Now, it's quarks, again, that make up the protons and the neutrons. And quarks have mass. The mass of the quarks inside the atom has to be very exact for life to exist. For example, the mass of the up quark, which is one of the quarks that makes up protons and neutrons, an up quark, the mass of the up quark has to be fine-tuned to 1 part in 10 to the 23rd power relative to all the possible masses that a quark could have. To imagine how small this number is, imagine a fraction divided by a 1 with 23 zeros after it. This, in terms of percentage, is a decimal point, then 20 zeros, then a 1. So that a 1, that's 21 places to the right of the decimal point in terms of percent. So if the mass of an up quark were this tiny, tiny fraction larger or this tiny fraction smaller, there would be no life. Now, as you know, atoms also contain electrons. When we look at the possible values for the mass of the electron compared to the masses of the up and the down quarks, down quark is another type of quark that's in a proton or a neutron. So if we compare the masses of the electron to the masses of the up quark and the down quarks inside the nucleus, there's only a very small range of values that allow life to exist. You can see on the chart there's only a tiny sliver of allowed values compared to all the possible values that the masses could be. There's no underlying reason for this, and we can't explain it in terms of anything else. Now, the mass that a quark has is actually only a tiny fraction of the mass. To 2% of the total mass of an atom is due to the mass of the quarks inside the protons and neutrons. The rest is energy. It's the kinetic energy of the quarks that are moving around very rapidly, and the potential energy of the binding energy that's holding the quarks together. So energy contained within the protons and contained within the neutrons, that makes up most of the mass we experience. And this energy also has to be very fine-tuned for life to exist. So quarks have mass. Quarks also have a charge. Since they have a charge, they experience attractions and repulsions. In other words, they experience the electromagnetic force, which means they have to absorb and emit photons. Now, 2 up quarks, which are both positive and exist in the proton, and 2 down quarks, which are both negative and exist in the neutron, they should repel each other because like charges repel, but they don't. This is because they also experience the strong force, which is much stronger than the electromagnetic force, hence the word strong force. So it's the strong force that dominates inside the nucleus. Back to charges for a moment to point out an interesting fact. The electric charge of the electron, which we write down as -1, must be exactly equal and opposite to that of the combination of two up quarks combined with a down quark, which we write down when we add all that up as the charge of the proton, which is +1. So quarks have mass, quarks have charge, and quarks also have a property called spin. This is an intrinsic property of quantum particles. It's a type of inherent angular momentum that affects the behavior of a particle in a magnetic field. It doesn't mean that it's spinning, it's just that the particle has this inherent angular momentum that can point one direction or the other. So quarks have two possible spin states that we call +1/2 and -1/2. Now you might remember from chemistry in high school that the +1/2 and -1/2 states of electrons, you may have represented them as two arrows. Well, that's what organizes the electrons into their orbitals, and it's what allows for all of chemistry to occur. Now, this organizational principle, called the Pauli exclusion principle, governs all the behavior of particles that have a half-integer spin, which we call fermions. The Pauli exclusion principle says that two identical fermions, particles with a half-integer spin, cannot be in the same place at the same time. So this half-integer spin of quarks, the fact that they are fermions, plays a part in the organization of the quarks within the nucleus. The spin of the quark affects the probability of finding a quark in a particular location within the nucleus. Quarks spinning in one direction tend to gather on one side of the proton or neutron, while quarks spinning in the other direction gather on the other side of the proton or the neutron. So particles which make up the nucleus are part of a very complex system. They have a rich, you could even say designed, internal structure. Now this property of spin also means that particles made with three of the same quarks shouldn't exist, but they do. In fact, we found one called the omega- particle. Now this is why quarks needed another property called color, which we'll look at in a minute. There are also particles in the nucleus called gluons. Gluons have a spin too, but they have three possible spin states, not two possible spin states. This means that they don't have to follow the Pauli exclusion principle. You can cram a whole bunch of gluons all together in the same location, but not quarks. This design of quarks not being able to be in the same location, but gluons not caring if they're in the same location, that design is absolutely crucial to the structure of the atom. Gluons bring us to the last property of quarks. Quarks have mass, charge, spin, and a property we call color. And color is what carries the strong force. Now we had to invent this property to explain why quarks don't violate the Pauli exclusion principle. So just like charges dictate the attraction and repulsion for the electromagnetic force, color is what dictates the attraction and repulsion for the strong force. And here's how it works. Quarks carry three types of color charge: red, green, and blue. And these actually aren't colors like what we see. We just needed three things that cancel out. And the primary colors, red, green, and blue, all cancel to make white. So just like plus and minus charges are two things that cancel, and we needed that for the electromagnetic force, we chose color for the strong force because we needed three things that cancel. Now quarks carry three types of color: red, green, and blue. There are also particles called antiquarks that carry three types of anticolor, called anti-red, anti-green, and anti-blue, or sometimes going by cyan, magenta, and yellow. Gluons carry both color and anticolor. So a gluon can carry a red anti-green or a red anti-blue. And there are also three colorless glutons that carry a red anti-red and a green anti-green. So color carries the strong force. And remember, the strong force is way stronger than the electromagnetic force, like 100 times stronger. The strong force also works in two different ways to keep the quarks together and also to keep the nucleus together. So here's how strong force interactions keep the quarks together. They do that through an exchange of gluons that only can operate over a very short distance, 1 femtometer, which is 10 to the minus 15 meters. And this force actually gets stronger as the particles get farther apart. It's like a rubber band. As it gets farther and farther apart, the force gets stronger and stronger. And as you get close together, the force gets weaker. So it works like this. A red quark can emit a red anti-blue gluon and turn blue. A blue quark can absorb a red anti-blue gluon and become red. Or a blue quark could emit a blue anti-green gluon and become green, and so on. So this exchange of gluons and the changing colors of quarks is what keeps the quarks together to make a proton or a neutron. So protons and neutrons are not simple things. A proton and a neutron are both seas of gluons forming quark-antiquark pairs in a chaotic dance mitigated by charge, mass, spin, the strong force, electromagnetism, and a property called color. A proton exists when you have a net combination of 2 up quarks and a down quark, each of a different color. A neutron exists when you have a net combination of 2 down quarks and an up quark, also each of a different color. Quarks emitting and absorbing gluons is what keeps them confined, and it's what makes a proton or a neutron. Now, gluons can also spontaneously create a quark-antiquark pair. Sometimes this happens as the gluon strays outside of the proton or neutron. This quark-antiquark pair can then be transferred over to a different nucleon, switching a proton to a neutron or switching a neutron to a proton. We think this exchange of particles, this exchange of quark-antiquark pairs, is what overcomes the proton-proton electrical repulsion and is what holds the nucleus together. So for an atom to operate in a manner that can produce life, the nucleus needs several characteristics. Number 1, the mass of the quarks, as well as the energy confined inside a proton and a neutron, must be exceedingly fine-tuned. Number 2, the positive quarks in the proton and the 2 negative quarks in the neutron should repel each other because of their charge, but they don't. Also, the sum of the 3 charges on the quarks that make up a proton must add up exactly to the charge on the electron. Number 3, quarks have a property we call spin, and that helps to organize the quarks within the nucleus. Number 4, to help explain how the quarks stay together, we needed another property that we called color to explain how the strong force works. But for color to work inside an atom, there had to be 3 quarks making up a proton and a neutron. Number 5, quarks have the ability to emit and absorb gluons that enable the creation of color, the strong force charge. Gluons only exist if quarks exist, but quarks can also appear from gluons. Number 6, gluons must have the ability to form quark-antiquark pairs to mediate the strong force between protons and neutrons and keep the nucleus together. Protons and neutrons must then be able to combine in specific ways to create all the different elements that we're aware of. Number 7, the strength of the forces involved are only allowed to be in a very narrow range of values for life to exist. If you compare the possible values for the strong force to the possible values of the electromagnetic force, there is only one possible combination that will allow for life to exist. All of this must work together. Atoms are a marvelous piece of precise engineering. Several very specific features are necessary to create and dictate all the actions and all the parts and all the forces that make up the atom's nucleus. Many of these factors had to arise independently and then combine and then interact with each other correctly, all within the first moments after the universe began. The entire atom all works together. In other words, it's irreducibly complex. If any of the parts were missing or if any of the forces were different, we wouldn't have life. The atom is a highly coordinated and purposeful arrangement of parts that only works as the base unit for life if the mass, energy, charge, spin, color, and strength of forces are all within a specific range of values and are all able to do a specific job. The atom is an engineered system that appeared in its current form within minutes after the beginning of the universe. So why is this important? Well, it looks like life in the universe is not an accident. A reasonable conclusion from what we've learned about the nucleus is that it was designed specifically for us to exist. And if that's the case, someone had to design it. The only thing we know that can design and implement an engineered, multifaceted, purposeful arrangement of parts like an atom is a mind that is capable of making free will decisions, a person. This would mean that the most fundamental fact in the universe is a person, that personhood came first. Christians believe that this person is God and that the universe was made by God for his own reasons. He designed and built the atom right at the beginning of the universe. This gives us incredible intrinsic and objective value. God was working and planning from the very start for us to be here right now, for you to be here right now. This gives us meaning and purpose that are grounded in God's reasons for creating us. We have value, we have meaning, and we have purpose that is totally independent of what we are able to accomplish, or what we're able to do, or what we can't do. God's reasons for creating the universe and creating us culminated in the person of Jesus. Jesus came to earth to mend the fractured relationship between us and God. Because we constantly break God's law, we're separated from God. So God provided a way to repair this relationship through the person of Jesus. God, the creator of the universe, wants a relationship with you. And you can have that relationship through the person of Jesus. So the exquisite fine-tuning of the nucleus of the atom, looking as if it's designed specifically for life, for us to exist, can point us to the person of God. God cares about us. He cares about you. He cares about you so much that he wants you to have a relationship with him. And you can have that through the person of Jesus Christ.